Example 6 says, for each of the following, part A, find the absolute extreme of f and where they occur. So A absolute means A max and then A min. Give myself some space to write the answer later. B, find any points of inflection. So B, we want inflection points. And then C, it says sketch it out. All right, so we are going to make a grid. Let's see, on the x-axis, it goes from 0 to 2, but let's read this on, okay? F is an even function. It has to be continuous from -3 to 3 and has the following properties. So if it's -3 to 3, I'm gonna go 1, 2, and 3, 1, 2, and 3. And now an even function, students, this is going to be a reflection over y-axis. Okay, so whatever you have on the right side, you must reflect it over the left side and vice versa. Okay, so let's go do a couple of these. So when x is 0, y is 2. So I'm gonna go make 2 tick marks on the top. When x is 0, y is 2. When x is 1, y is 0. So when x is 1, y is 0. Now remember, it's an even function. So whatever you have plotted or graphed on the right side, you do it on the left side as well, and vice versa. When x is 2, y is -1. So I gotta go and make a -1 tick mark here. When x is 2, y is -1. And again, students, make sure you reflect it, okay? Okay, so now let's go find what's happening. From 0 to 1, let's focus on that. From 0 to 1, you have a positive y. Your first derivative is negative and second derivative is positive. Positive derivative means it's concave up. All right, so let's see how we are going to graph that out. From 0 to 1. So I'm going to highlight 0 to 1 here. So 0 to 1 is this part, okay? I will erase that in a little bit. We have a positive y that's concaving up. So positive y, something like that, okay? So, and if concave up, and even doesn't have to be, okay, just like that. Okay, so done with that piece. I would now erase my white highlighter part. Okay, so now we are going to attack, and reflect it, students, to the other side. Now I'm going to get a blue pen here. Now let's focus on from 1 to 2. 1 to 2, y is negative, okay, y is negative. First derivative is also negative. That means the slope is negative. And then double derivative is negative. So double derivative means this is now concave down. Okay, so now we're going to go y is negative and slope is still negative. So now concave downward, just like that. So I'm going to go over here and do the same thing. From 2 to 3, here's 2 to 3, y is still negative. The slope is now positive for first derivative and concave down. Okay, so now I'm having to graph this below the x-axis because y is negative. The slope is positive and concave down. So I'm going to go like that. Now it doesn't say at 3, students, it doesn't say where the y value is. So you can land this however you want as long as it's y value maintains negative. So I'm going to go just like that. Okay. And it's an inclusive here. So I'm just going to go and close that dot. And that's what I'm going to do with this side. Okay, so now let's go check the rest of this. We have to go and verify everything else is going to be okay. At 1, you should have a derivative right here, okay? That's 0. That means it's smooth and horizontal, and double derivative is also 0. So if it's not smooth before, I would just try to make it more horizontal, just like this. Okay. So remember, the slope is 0, so I want to make sure this is nice and horizontal, more horizontal, because we want to demonstrate that that's getting closer to the derivative of 0. And then at 0, first derivative doesn't exist, okay? So at 0, that means there's a sharp turn somehow. Oh, which we do. Okay, so make this into, at 0 here at the top, make it into a sharp turn. Same thing at 2. The first derivative and second derivative doesn't exist, so make these ends right here sharper. So it could be a corner or cusp, it doesn't really matter, right? Because it doesn't say. So this is how you guys sketch it out. So now let's go and state the A max. A max, meaning that that's the highest that we're gonna have. So A max is, the location is at 0 and the Y value is at 2. So is 2 at X equals to 0. We have 2 absolute min here. 2 locations, so but the value is the same. So A min is -1 at X equals to -2 comma +2. Now next is looking for inflection point if we have any. Remember, inflection point is when the concavity change from positive to negative or vice versa. So I'm going to erase a lot of these here and just kind of highlights the double derivative. Okay, so as you guys see, we only have 1 changes here, which is from positive to negative, and that is at the location of 1. So we have 1 point of inflection. Okay, so we're gonna have, it's gonna be X is 1, but remember it's a reflection, so we wanna go to the other side and write that as well. So 1, and then the Y value at 1 is going to be 0, and then go to the other side and write the same thing because it's an even function. And that's all of the questions, I believe. All right, guys, so let's do another one just so that way we get more practice in. Okay, so part A wanted us to find absolute max, absolute min. Then part B wanted us to find inflection points if we have any of these. Part C wanted us to graph it out, but let's see how we should be scaling our grid. So looks like we would need only from 0 to 3. So I'm just gonna make most of this on the positive side. 1, 2, and 3. And then the Y values are, let's see, we got 1, 3, 0, and -1. So I'm gonna make 1, 2, 3, and then -1 down. Okay, so let's start with 0 plotted at 1, 1 plotted at 3, 2 plotted at 0, and last dot is 3, -1. So these are all of the F points. Okay, then let's see, it says here first derivative. So let's take 1 box at a time. Okay, guys, so from 0 to 1, Y has to be positive. First derivative is positive because, so that means the slope is positive. And then second derivative is positive. That means it's concaving up. So that is going to be from here to here, okay? Concaving up, slope is positive. It's above the x-axis, so y is positive. Perfect. Let's take the next interval. 1 to 2. Y has to be above the x-axis because it has to be positive. Your slope has to be negative and concaving down since the double derivative is going to be negative. So concave down. So how would I concave down? Okay, I'm going to make this better later, but right now I'm just going to go one piece at a time. Then the third interval. Ooh, can you guys change this to 2, please? So that's 2 to 3. So the third interval is from 2 to 3. Y is negative. Slope is negative and concave down again. So y is negative, meaning that I'm going to be below the x-axis, concaving down. So it's going to be something like this. Okay, so now I'm going to go in and then check the other stuff, such as, okay, what's going on at 0? At 0, y is 1. First derivative is going to be at 2. So that means the slope is 2. And then second derivative doesn't exist. Now, this is the part where I really want to double check right here, okay? At 1, the derivative doesn't exist and double derivative doesn't exist, so, okay. And then here at 2, everything is 0, including the first derivative. So what that means is I want to make this 2 spot really smooth, okay, guys? So let's see if I can make that more horizontal because the slope of 0 is really my concern. I want to make horizontal. Oh. Geez, can I do that without? there. Okay, so try to make this as horizontal as you can. Obviously, this is sketched by hand, so we're not going to get a perfect graph, but that's what we're going to have. All right, so now let's go look at our max and min. We do have a max location here. So max is 3 at x equals to 1. Min is down here, absolute min. Min is -1 at x equals to 3. All right. So then we want to look for inflection point. So students, when it comes to inflection point, I'm just going to look at the second derivative, and it's going to be here. The concavity is changing from positive to negative and vice versa. And that change is happening at the x value of 1. Okay, so here's x value 1. That's also your maximum point. So it concaves up and then concaves down. So that is an inflection point, and that point is 1, 3. Now, some student might argue that this is an inflection point. That's not true, guys, because it's not changing in concavity, right? It's down and then down again. So make sure we're cautious about the changes in concavity when it comes to inflection point, and that's example B. All right, guys, so sometimes we can even use the second derivative to find your local min and local max. Are you guys ready? This test has limitation though, so listen up. This test requires us to know f prime only at C, which makes it easier to apply. But the limitation is that if f double prime fails to exist, then we have to go back, then use f prime test. So we have to go back to first derivative test. Okay, so here's the second derivative test. If f double prime at C, if f prime of C equals 0 and f double prime at C is less than 0, then f has a local maximum at x equals to C. Now, if f prime at C equals to 0 and f double prime of C is greater than 0, then f has a local min at x equals to C. Okay, so here's an example. I'm gonna show you both methods, first derivative and second derivative, and then you can see, you know what, sometimes first derivative is not bad, sometimes second derivative it's easy, okay? This one, they already gave us first derivative, so all we have to do is set equals to 0 to find our critical points. Take each factor, solve for x. Okay, so we have 3 critical points. The first one's 1, the second one is 2, and the third one is going to be at 4. I'm going to make 2 number lines. The first one is for first derivative, 1, 2, and 4, not to scale whatsoever. I'm also going to make a number line, students, for second derivative. All right. Now, we can right now go and find local min and local max with first derivative. So we knew first derivative, these are all the zeros of first derivative. So we just need first derivative, left-hand behavior, first derivative between 1 and 2, so that's 1.5, so 3/2. First derivative between 2 and 4, so that's going to be 3, and then right-hand behavior of our first derivative, okay? And all we are looking for is positive and negative. So when I plug in -100, again, to this equation, -100 minus 1 squared, that's going to be positive. -100 minus 2 is negative. And then -100 minus 4 is negative. So that is going to be, when we multiply, that's positive. 3/2 minus 1 squared, that's positive. 3 over 2 minus 1, that's going to be, minus 2, I'm sorry, is negative. 3 over 2 minus 4, that's also negative, so that's now still positive. So positive, positive. When we plug in 3 minus 1 squared, that's going to be positive. 3 minus 2, that's positive. 3 minus 4, that's negative, so that's negative. And right-hand behavior, that's going to be positive, positive, and positive. All right, guys, so ready? I'm going to write down the L-min and L-max. So A is looking for local max, so L-max. And if you guys remember first derivative, the local max is when the first derivative changes from positive to negative, all right? So here is where it changes from positive to negative. We have one location, so L max is at, not is, okay, at 2. We don't have we don't have the original function for us to plug it in. So we can only give the x location. Find the points, okay, which is just x right now since we don't know the actual f of x to plug in. Now B, it says L min, and if you guys remember, local min is when first derivative changes from negative to positive. All right, so I'm going to erase my previous two circles. We're gonna go, here's negative and it changed to positive. So L min is at x equals to 4. So that's not too bad. Now the third piece, the third question here is looking for inflection point, students, so IP. The inflection point, we want double derivative, okay? Inflection point is when double derivative is positive on one side and negative on the other. Now we also, or vice versa, we also want to use the second derivative, honestly, students, to double check our L max and L min, and you're going to see, oh, you know, second derivative for this one is easier. Or maybe not. All right, let's do second derivative, f prime prime. But before we go to f prime prime, we have three terms here in the first derivative. What I want to do is you can do two things. You can FOIL all of this out, okay, and then do the power rule, or you can keep the first x minus 1 quantity square and then FOIL the second, so that way you would only have two terms, okay, FOIL the second, and then you can do the product rule. So when I FOIL x minus 1 quantity square, I'm gonna get x squared minus 2x plus 1. And when I FOIL x minus 2 times the quantity x minus 4, I would get x squared minus 6x plus 8. Okay, so from here, I'm gonna use product rule. Are you guys ready? Derivative of the first, which is u, which is gonna be 2x minus 2 times v, so copy this down, plus v prime, so that's gonna be 2x minus 6 times u. So from here, we are going to FOIL and then combine like terms. Now, I did all the basic math on my paper already. You guys should try to practice to see if you guys come up with the same answer. After all the basic math, I get 4x to the third minus 24x squared plus 42x minus 22. And I'm gonna set it equal to 0. All right, I'm trying to solve for x, but this one's not factorable. Now, students, if I give you a question that's non-calculator, then it has to be factorable or it has to be easy for you to solve without one. But since I just kind of stole this from your book, it's not factorable, so I'm just gonna find a calculator and graph it out. And lucky for us, I already entered that in just to save time. And so we have 3 zeros here. One is at 1, this one is 1.634 and 3.366. So those are the 3 zeros. Let's go back and write them out. So I'm gonna write use calculator. Okay, so x equals 1, and then the next one is 1.634, and then 3.366. All right, so earlier we got this answer, guys, from first derivative test, but technically the second derivative test sets, right? if f prime of 2 equals to 0, which that's how we get the 2, and then when we plug in second derivative with the x equals to 2, it has to be negative, and then that means it's a local max. Well, for the sake of simplicity, because honestly, I don't want to sit here and plug 2 into that equation. So if we go to the graph that we graphed earlier, and as you can see, right, when x equals to 2, it is negative here in bottom. Can you see this? So that's why it is confirming with the second derivative test. Now, sometimes if it's an easy equation and you can get the second derivative quickly, then the second derivative test is super useful. In this case, it took a little bit of time to do the second derivative test. Same thing with the second derivative of local min. The local min said, okay, when you take the first derivative, right, and you said it goes to 0, and then you get this value of c, and you plug that value of c into the second derivative, if it's positive, then you know that value is going to be a local min. Well, we got a value of 4. So if we go to 4 here on x, I'm going to pinch it here. We know at 4, I'm up here somewhere, right? So let me go even further up here. So that's around 4. That's definitely positive. So you can tell that the second derivative is true and is backing up the answer with the first derivative. Now, inflection point, guys, it's when the second derivative is positive one side and negative on the other, or vice versa. So we want to make sure we draw that here so we can find your IP. We got 1 is going to be at 1, then 1.63, then 3.37, and these are ugly numbers, so we are definitely going to use some help here. All right, end behavior in between 1 and 1.3 is 1.5, and this is an ugly equation, so I'm gonna definitely need some help. And then in between 1.63 and 3, I'm going to do f prime of 2 and then write end behavior. All right, we have to plug it into the second derivative. We can even plug into here if we want. All right, so let's plug into here. It seems a little bit friendlier. Negative 100 times 2 minus 2, that's going to be negative. Negative 100, and then all of that square, that's going to be positive. And then plus, okay, you know what? Since I already have the graph out, can we just use my graphing graph here to see what's happening when we plug in negative 100? When we plug in negative 100, would you agree that's negative based on this graph? Because it goes downward. So just for the sake of simplicity, and I promise you, if it's an ugly number in your homework, you can use a calculator. Now on the test, if it's non-calc, believe me, I will give you friendlier numbers, okay? And then 1.5, if I plug in 1.5, whoa, I can't pinch, okay. So 1.5, it's somewhere here. That's 1.0, this is 1.6, so 1.5 is here, here, here. There you go, around there. There you go, it's positive 0.5. So we know it's positive. And let's go to 2. 2, it's here, and we know it's negative because it's down here somewhere. So let's go back. Negative, and write end behavior of double derivative. It goes up, so we know that's going to be positive. All right. Now you can also use your calculator and punch it in and get the same exact answer. So let's see. Ready? We got negative, we got positive, we got negative, we got positive. Oh wow, it changes quite a bit. Okay, because it changes, first inflection point is right there. Second inflection point's right there, and third inflection point's right there because it kept changing. So IPs are x equal 1, 1.63 and 3. I'm gonna round it to 3.7. All right. All right, here's B. Y prime equals x minus 2 raised to the power of 2 times x minus 1. So this one does not look as scary as, example, A, right? So let's write down all the things that they are asking us to find. I'm sorry, the first one was L max, then B was L min, and C was the inflection points. And just to remind yourself, remember, if you're working on your homework, it's always a good idea to write these rules out, because when it comes to your exam, it's a lot quicker for you to finish a problem if you can recall these formulas or theorems from your memory, okay? So at local max is when you have the first derivative going from positive to negative, or when you plug in your second derivative and it's negative. Same thing with L-min, when we have first derivative going from negative to positive, or when the second derivative is positive. The IP is when second derivative, so IP, spell this out, is when the second derivative goes from positive to negative or vice versa. So the first thing we want to do is set this equal to 0 to find the critical point. So we have two critical points here. Let's make your number line. You don't have to do the number line. I do number line for organization. We knew that 1 and 2 are when the first derivative equals to 0. So we just have to find left end behavior in the middle somewhere, which is like 1.5. And then right end behavior, okay? So when we plug in negative 100, negative 1,000, negative 1 million, and we square it, this is going to give us positive. And we plug that in there, that's negative, so this is negative. 1.5 minus 2 squared, that's going to be positive. 1.5 minus 1, it's positive. So in the middle is positive. On the right side, everything's squared. On the first one is positive, and then this is positive. So on the right side, it's all positive. So as you can see right away, we do not have any interval that goes from positive to negative. So for your local max, you have none. Local min, we are going from negative to positive. So here's negative, and we went to positive. So we have 1. So local min is at, remember at is x location, at 1, okay? Well, IP, then we would definitely need second derivative. Are you ready? So second derivative, u prime is 2 times x minus 2 times v, and then plus v prime. V is x minus 1, and the derivative of that is just going to be 1, so we are just left with this. Let's distribute. So y prime prime equals, if I were to distribute that, I would get 2x squared minus 6x plus 4. Distribute that, we would get x squared minus 4x plus 4. And combine like terms, so 3x squared minus 10x plus 8. Okay, now if this is factorable, you factor it out, but if it's not, yes, I do expect you to work this out without a calculator. You can use your calculator for basic math, but in regards to the rest, do it without one. So the quadratic formula says negative b, so it's going to be 10 plus or minus b squared, so that's negative 10 squared, it's 100, minus 4 times a times c, which is 8 all over 2 times a. So this is going to be 10 plus or minus. Under the radical is going to give me 4 over 6. That's not too bad. So x is going to be 10 plus 2 over 6, or x is going to be 10 minus 2 over 6. This will give me 2. And this is going to give me 4 over 3. All right, I'm out of space there, so I'm going to do it, my number line. I like number lines, I don't know why. You guys might hate it. All right, f double prime of x is, I have two values, 4/3 and 2. I'm going to do f double prime of left end behavior, f double prime somewhat in the middle, so 1.5, and f double prime of right end behavior. All right, right and left end behavior, this is the easiest because I only need to worry about the power function. So that's square, so everything's going to be positive. Now 1.5, it's easiest if I plug it into here because I don't have to do a lot of work, okay? So 2 times 1.5 minus 2 is now a negative half. 1.5 minus 1 is a positive half, plus 1.5 minus 2, that's going to be negative half, but square is a quarter. So cancel that out. I have a negative half left, which is negative 2/4 plus 1/4, so that's a negative. Okay. All right, so ready? Again, inflection point when the double derivative goes from positive to negative or vice versa, negative to positive. So both of these students are inflection points. Okay, so we have 2 inflection points and no L max and 1 L min. Example 8. Sketch a smooth curve y equals f of x through the origin with the properties that f double prime is less than zero for all x less than 0, and f double prime is greater than 0 for all x bigger than 0. So as you guys remember, the double derivative, okay, when it's telling you that we're going from negative to positive, this is talking about, so f double derivative is talking about concavity which means we're talking about inflection point. Okay, so it's concaving differently and then at 0. So we are going from, on the left side of 0, it's concaving downward, and on the right side it's concaving upward. So it looks like we have an inflection point at x equals to 0. So that's it. That's just that easy for A. Now on B, I understand that if you guys printed your notes earlier, this is not going to be here. Neither these graphs here. So can you guys take a minute and sketch it in or write it in before we start? If we have to, can you just pause this video, copy all of those down, okay? B, sketch a continuous, okay, mind you, continuous curve of f equals f of x with the following properties. Label coordinates where possible. So I'm gonna go, looks like our x values here is less than 0 all the way to beyond 5. So I'm gonna go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the y value goes up to higher than 8. So I'll go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So here's the description. On the left side, okay, of 0, it says falling and concaving up. Falling is describing the slope. Okay, falling is another way of saying decreasing. Okay, so on the left side of 0, it says falling and concaving up. And the next time it says, okay, well, at x equals to 0, I'm gonna go up 2. I'm gonna do all the ones I know how to do. And then 3, 5, ooh, I have an inflection point, okay? So 3, 5, make sure 3, up, 2, 3, 4, 5, right there. Make sure I keep that in mind. 5, 8, horizontal tangent. So it looks like, students, we have 2 horizontal tangents. So make sure I keep that in mind, okay? So 5, 2, 4, 5, and then this was by 10. So there you go. So if I have a horizontal tangent and I have an inflection point at 3, 5. So falling, concaving up, all the stuff on the left side. So concave up must go like that, and that slope is falling. Perfect. And then next at 0, 2, I have a horizontal tangent. So guys, I had to round that out. And from 0 to 3 here, the slope is increasing and concaving up. So increasing and concaving up. So it goes like that. Okay, so I'm gonna erase this slightly. Concaving and, okay, perfect. At 3, 5, I know I have an inflection point. So that means on the other side, it should be concaving down, right? So that's exactly what it should say. Rising and concaving down. Just like that. And then I have a horizontal tangent, meaning that I should be roundabout, and then exactly what I expected, falling, which is decreasing and concaving downward. Voila! And that's how you sketch, baby. Okay, guys, so this section was quite long. Okay, so let's try to put a summary together. Okay, this is what this whole section is really about. Number one, differentiable function, let's call it y equals f of x, means f of x is smooth, continuous, and may or may not have increasing or decreasing interval. Okay, so how about first derivative test? Y prime, that's positive, meaning increase from left to right and maybe wavy. Okay, so if your first test is derivative, it may have an increase and it may be wavy. Okay, this is an f of x function. Now y prime, that's negative, it means it's a decreasing function, so decrease from left to right, and again, and maybe wavy. So your could be like this. All right, so again, this is f of x. We're using first derivative to test about increase, decrease. Now second derivative, y double prime, that is bigger than 0, we are talking about concavity. Okay, so if it's positive, concave up, should have no waves, and f of x may rise or fall. Okay, what does that mean? So here's f of x function, concave up. That means that's increasing, as you can see. And then it also have a concave up, but could be a decreasing function. Okay. Now double derivative, if it's less than 0, we know by now that it I can't spell concave. Like concave. Look at that. Concave down. Okay, no waves. And f of x may rise or fall. Okay, similarly, we know that it concaves down, so this is an increasing function. And then this is going to be a decreasing function, even though it's concaving down. So concavity does not necessarily equate to increase or decrease, right? Now 6 is your inflection point, which also deals with double derivative. Okay, inflection point is when double derivative sign changes. And remember, tangent exists, right? Because first derivative must exist. So something like this. Oh, there you go. That's your IP. We could also go the other way. All right. But the most important part here, guys, that the tangent f prime of x exists. Okay. 7. Y prime changes sign that means f of x has a local min or a local max, okay? So two cases, if it changes here, this is increasing to decreasing, so there's an L max. If it changes from decrease to an increase, then you are going to have an L min, okay? So this is L max, and this is L min. 8. If y prime equals to 0 and f double prime is negative at x equals to c, then f of x is a local max at c. Okay? So L prime equals to 0, meaning that you have a horizontal tangent, right? And it's a horizontal tangent. And if this is talking about double derivative, that's talking about concavity downward. So concave down. So if it's talking about concave down, then obviously this will be a local max. Last one. If you have y prime equals to 0 and double derivative is concaving up, which is positive, at x equals to c, then f of x is a local min at c. Similarly, right, if you got y prime being 0, that means you have a horizontal tangent, and double derivative is positive, that means you're concaving up. If you're concaving up and you have a horizontal tangent, then this would be an L min, and this I'm going to write L max on the top. And that's everything that we study in pretty much the first 3 sections, right?